This is what we're going to do today, of course. Just take a couple of these exercises, go through them. There are some mathematical exercises, there are some physical exercises. Of course, the physical exercises come with their own bunch of mathematics. So we just go through a couple of them, see how things go in practice. Now, I hope that what you have seen, even though it costs us a certain amount of mathematics, that we've greatly simplified the theory of electrodynamics now. All of it became extremely simple. And for quick reference, maybe it's a good idea to just have a little summary here. And of course, what I'm writing down now is something that all of you now should know quite well, that there's 4 of these Maxwell equations that tell you how electric fields and magnetic fields look. The divergence of the electric field is equal to a charge density with some number, maybe epsilon 0, depending on your unit system. The divergence of the magnetic field is equal to 0. The curl of the electric field is, in the most general case, given by minus the time derivative of the magnetic field. And finally, the curl of the magnetic field is given by the current that happens to be flowing plus a number times the time derivative of the electric field. Now, the physics should be completely clear to you now. A divergence you should see as a physical intuition as how much of it is sticking out. How much electric field is sticking out all depends on how much charge you have. It sticks out radially per charge. There's no magnetic field sticking out, which is another way of saying that they all come back, which by itself is another way of saying that there's no magnetic monopoles, right? Because they always curl back to where they came from. You can make an electric field by shaking an the other way around. You can make an electric field by shaking about a magnetic field and the other way around. That's what they say. Now, the great simplification that we did a couple of days ago was that we saw that all of this can be written down in a much more mathematically elegant way, namely in terms of potentials. And yes, potentials are somewhat more difficult to understand physically, but mathematically gives an enormous simplification. I'm not going to do the static versus dynamic case, I'm just going to do the general case now. It was the following. We found, just by using the mathematical aspects of vector calculus, that the electric field can be written as the gradient of this new thing that we call scalar function, scalar potential. The minus is completely conventional. The magnetic field is given by the curl of this other new thing called the vector potential. This was for the static case. Dynamical case says, well, you also have to do this. That's the idea. So instead of having to find your electric field and your magnetic field, you just find the scalar potential and the vector potential, and via these steps then you get your electric field and your magnetic field. Now, why would you do this rewriting? And I hope I convinced you of this, that first of all, the mathematics becomes easier in the sense that these 4 equations, where the e's and the b's are scattered all over 4 of them, you now get 2 equations, each of which tells you just the information about one of these scalars, one of these potentials, the scalar or the vector. Now, they came in a very difficult expression. Right? We had 2 differential equations that they were difficult, but again, lots of mathematics. But we showed a couple of days ago that you had a certain freedom in choosing your a's and your phi's, and we found that you are allowed to change the value of your phi's and your a's in a very specific way, in such a way that you would still get the same E field and B field. In other words, the same physics, the same experimental predictions. And you can use this freedom, it's called a gauge freedom. You can use this freedom to greatly simplify the differential equations that that phi and A obey. Now, one particular choice that we saw that was the Lorentz gauge. And then we saw that in the Lorentz gauge, things became extremely simple. We found that the scalar potential is given by this differential equation, is rho over epsilon 0. And in this Lorentz gauge, the vector potential is given by the exact same differential equation. It's just that all scalar potentials are replaced by vector potentials and charge density is replaced by current. And there you go. course, all of this you have heard before, but it's good warm up. Great advantage. The E's and the B's are not scattered over multiple equations. They're now separate equations, completely uncoupled. Just solve this one, solve that one, you're done. Once you have your phi's and your a's, put them back in here, you get your e's and your b's, as if you had solved these. Extreme mathematical convenience, especially if you know what the general solution is to these equations. Now, I've given you the general solution in the static case. So this is all this big summary of a couple of days ago. In the static case, in other words, that the time derivatives are all 0, you just put your hand on these, then you found that phi is given by this integral 1 of 4 pi r, this, and your vector potential is given by. And by now you should fully understand what I mean by all the different types of r that are in there. So not only have we completely simplified all of our physics, I've even given you now the full solution to every single situation that you would encounter. Of course, in the static case, you can ask yourself the question if there's a similar general solution for the dynamical case, and there is.
So this question was asked in the lecture as well, but just to remind, what was the physical meaning again of the scalar potential and the vector potential?
Well, the question mostly was, is there a physical meaning?
Yeah.
And there was sort of a semantic issue there. Yeah. Sort of a semantic issue there. I mean, at what point do you say that something has physical meaning? If you want to translate back to something you can measure, then very little things in physics have physical meaning. Right? Forces do not even have physical meaning, because what you measure is not how much force you feel. What you measure is the effect of the force on your acceleration. Acceleration are meters and seconds. Yeah. So in that sense, I would say that probably only the things that are really measurable might be time and space, and the rest are just derivatives. I mean, name me any physical observable.
Yeah.
Temperature.
Okay.
No,
Well
that's also not directly measured, because you're actually measuring the kinetic energy of your molecules.
Yeah. What is kinetic energy? I mean, energy is a very good example of something that you also don't really measure, right? I mean, if I lift up this cup of coffee onto this height or something, and I ask you what the energy is, the only way that you get there is, there we go again, by measuring its height, meters, and the constant of acceleration, which again is meters and seconds, or seconds squared. Of course, you also have to measure the mass. So in that sense, there's very little things, very few things in physics that are measurable, are real. But this is just semantics. You might also just call it philosophical. I mean, to me, these fields are just as physical as these fields. Now, there is some objective way that we can look at this, and this is what we also did 2 days ago, and that is that in order to get your E's and B's, you have to do something with the A's and the Phi's. So in that sense, A's and Phi's are somewhat less physical than the E's and B's, because you have to do one extra thing to them to get to something measurable. So there is some objective hierarchy there, I guess. Now, if you ask me what is the physical interpretation of that, I would just simply say, well, there are these two things that give you the electric and magnetic field. But that's about as good as I can make it.
Okay.
Yeah, I mean, trust me when I say that your issue with this, with not really feeling what these things are, is just you having to get used to these new things. Because let's go back to energy, you say. All right? I mean, you're completely used to the concept of energy. What the hell is an energy?
Yeah,
how do you measure energy?
Yeah, like it makes sense to me because I've used it so much.
Yeah, exactly. If you use the things often enough, at some point they start making sense to you.
Yeah.
But if you come, I mean, again, this is mostly just semantics. But if you just go back to things, I would say that the only things that are really measurable are seconds and meters and kilograms or something like that. Yes.
In the Griffiths book, they said that these potentials could be described as the potential energy per unit charge.
Oh, okay. Yes.
But I don't see how I would come to that conclusion looking at those equations.
Okay, that is a good comment. Actually, it relates to your question. We can assign some sort of physical interpretation to these things, namely the potential. Focus on the scalar potential, and the idea for the vector potential is very similar. It is related to the energy of a charged particle. And you can already see how that works, because if you want to calculate how much potential energy you've given an object by pushing against it, you have to calculate this integral, right? This is work.
Yeah.
Now, of course, work is not exactly the same as potential energy. You have to be very subtle about these things. But if you assume that there's conservation of energy, that means that the work that you have done, which is another way of saying the energy that you've lost because you started pushing and pulling on things, must have gone somewhere. So at the moment that you've been pushing and pulling on things, this amount has to have gone someplace else. And suppose that all of this we have put into pushing against a charged particle, an electron or so. Again, you have to be very subtle about that, because it sounds like I'm saying that work is the same as potential energy. It isn't. But suppose, again, that all the work that I do is all converted into potential energy, no losses and such. Then you can already tell, so let's just call this potential energy. We've been using V for many things now. Okay. In fact, the Griffiths book actually calls this thing V. I decided not to. Okay, well, it's just like this potential energy. Okay. Now, you already know, and again, we're just looking at the static cases for simplicity now, that the amount of force that you need to push against an electron or charged particle is Q, a charged particle, times the electric field that the particle feels. So that would be this. Minus should not be there. Right? But we also know that E apparently is given as this thing. So apart from a minus sign possibly, you get this. And just very hand-wavingly, let's pretend we can just cross out the derivative and the integral. Of course, you have to be careful because it's a vector integral. But just to give you some idea, then this tells you that the Q that remains times this thing is a measure of the potential energy that a thing has. And that's the comment that Griffiths makes. So yeah, I mean, maybe here's somewhat more of a physical intuition for these things.
Yeah.
But you have to be very careful because I make a number of assumptions here. And that the work that I do is actually all converted into potential energy. And I think, but Sophie, you might have written that part of the book better than I have. I wouldn't be surprised if Griffiths actually makes a comment that you shouldn't completely see this thing as an energy. Apart from the factor Q. It's related, but it isn't the same thing. It's unfortunate that it's called a potential in that sense. And I hope that I've convinced you a couple of days ago why these things are called potentials. Not because they're related to potential energy. It so happens that it is under some conditions. They're called potentials because in physics, everything of which you take a derivative and then gives you something physical, we call a potential. Any more questions maybe? Because we're just doing a summary right now. None? Okay.
Wait.
Okay.
Where you plugged in the E field?
Yes.
Where did your
A field?
Yeah.
Yeah, I was just looking at a static case.
Oh, okay. Sorry.
Yeah, just to give you a short idea of why this is related to potential energy. But here again, you see why you shouldn't just see this as potential energy or a measure of potential energy per unit charge, because I'm throwing out this part now. So, yeah, I'm sorry. It's sort of like a non-answer if I say, well, the physical meaning of that thing is, well, take its derivative this particular way and you get your E's and B fields. But I propose that the only reason that you have more trouble seeing the physics of those things than you do, for instance, say about temperature or energy is really just because you're much more used to energy. Okay. Last time that we saw each other, I gave a couple of mathematical exercises to fill in the gaps of our reasoning. But I decided also to just throw in a couple of applications of this theory. It's not the main objective of this course, but maybe it's fun to do it anyway. And I hope that I convince you that if you do it in this way, using this trick, given that you already know the answers for every situation, you end up with a much more simple application. So I want to do two exercises. One of them is, what is the electric field at a certain distance from an infinitely long wire? There's a current, a charge in there, not a current. We've already done that exercise, but try it this way. Let's just see if we get the same answer. as a bonus, let's see if at some point then we get our electric field and our magnetic field, if they actually obey this rule and this rule, because they should. We built it explicitly in that these things, the scalar field and the vector field, already automatically fulfill this requirement, and in the static case, this is 0. So let's just see if that happens. So it's an exercise of which we already know the answers, but let's just see if we get the same results. Electric or magnetic? Which one do we do first? Want to do them both? Be very quick about this.
Electric.
Electric. Okay. So it's an exercise we've done before. Here's a wire, and the wire is such that every part of the wire has a certain amount of charge. Lambda, we called it in the previous exercise. The previous exercise, I think, was called 2.13 when we did it before. Let's go check. And otherwise, you can see it on the recording. Yeah, 2.13 it was. And suppose that you're standing over here and you want to know what is the electric field when you look at the complete, full, infinitely long wire. And we did some discussing 2 weeks ago on if you can already sort of intuitively feel what will happen. And then we saw, well, it will probably be a field that will point downwards and such. Right? Remember these things? And then we did the mathematics and we actually found that that was the case. Yeah, let's go and do it. So instead of calculating the electric field using these laws, let's just calculate the scalar potential. Note that we don't need the vector potential because it's a static situation. There is no magnetic field in the first place, let alone that it's varying, right? I mean, it's static charges. So not only is A 0, or is it's dA dt is 0, A itself is 0. Before this use the same nomenclature, I think we called this the z-axis. This is the x-axis, and this is the y-axis, and this is where we would like to know the electric field. Suggestions. And please don't let your response be, well, let's look up what the answer was when we did it by Maxwell's equations. Pretend that we've never done this exercise before. We want the electric field, so what object should we want to calculate first in terms of potentials?
Can we integrate? Can we take the...
Which one?
Like the
This one? That's one. Right. We, again, static case, so this is 0. So apparently all that we need for the electric field is just the scalar potential, and here's the general solution for the scalar potential. Again, huge simplification. We don't actually have to do the rewriting of these things, find the differential equation solution. It's already given, plain and simple, there you go. Okay, the phi at position r. Scalar thing is given by that integral. We proved it in tutorial 8 earlier this week. That this is indeed the general solution. 4 pi r is the integrate of all volume.
In the exam, for example, if there's like such an exercise, can we use the this formula, or do we have to prove this formula?
There will be some proof that this and this is true, so it's really based on mathematics, and there will be some apply these things, but not quite as difficult as the book sometimes makes. It's really just going to be of the simple kind that I'm doing right now, simply because, again, it's not the object of the course.
Okay.
But of course, I will always state in the exercise, do it by potentials or do it by electric magnetic field. So at the moment that I say do it by potentials, you're completely free to use this.
Okay.
Without proving that first. Okay, well, we have to put in the charge density for our particular situation. Integral 1 over r. This is a step that we've done before in different contexts. Instead of saying charge per unit volume times unit volume, write it as charge per unit length times the length, and the length that we're integrating over is z, yes? So there you go. And they've made our exercise simple. They've said that lambda itself does not depend on r, so that one goes out of the integration. Of course, because we're integrating over the whole of the wire, minus infinity and plus infinity. So there you go. Now, will somebody have difficulty calculating what this integral is? Yes? Well, it's good that we're here, so we're going to do it in detail. Regardless of the mathematical difficulty you might have with the resulting integral, we are able to write down the solution just like that. But sure, you still have to do the integral, that's right. Now we can do two things now. We can do this integration, and then we get a full expression that does not contain an integral anymore, some function with z's in there, right? And then we get phi, the exact same thing, but now not written as an integral anymore. We could do that, it's not wrong. What we could also do, we're not that much interested in phi, we're interested in the E field. We could also just take this thing in its integral form and perform this operation on it, and then get the E field. We could also do that. I mean, there's no necessity per se to first do the phi integration. You're happy to do it, by the way. But maybe for practice, let's do it, okay? Again, you don't have to. Because look, it's a derivative. It's an integral. You can already sort of feel that they're going to cancel each other out. You have to be careful. It's not a normal integral, it's a vector integral, so it might not be that easy. But sure, just for practice, maybe we'll just do this integration. I hope I've convinced you it's sort of superfluous work. Okay? But let's do it. What is R? Go to some place along the wire, the one that has a certain charge density lambda. The distance from here to there is of course exactly called z. The distance from there to there is of course exactly called y. So what we have to put in here is how many meters there is from this point to where you are standing. That was what big R always meant. So, Pythagorean maybe? Yeah. Okay. So we can already tell that R is just z squared plus y squared. Square root. What that means that our integration is exactly that. So I have to do that integration. Haven't we done one of these before? Integration like this?
Did we do that in the lecture?
Yeah. That's true. In my notes, I just went immediately to, let's say, to find the integral form and then do the gradient of the thing. But for practice, let's do the other thing. But it does require some real-time processes here. As you. Yeah. So out of sheer interest, do people have difficulty with integrations like these? I mean, you don't have to know the answer straight away, but suppose that you're doing an exam, say. Would you have difficulty finding what the answer is to such a thing?
I wouldn't know how to solve this one.
Stuff by substitution.
But there's many ways of doing it. Integration and the process of integration is sort of like an art and a science, in the sense there's no tricks that always work, as opposed to say differentiation. And it's just out of experience that I know it's probably going to be something like this. Then I try that in my head and see what I'm missing, and then just add correct for that. I didn't do it right here, right now, by the way. I was on a train this morning from Amsterdam here, and I like to do these little thingies, and came across this one. I did find it myself, by the way. It's just not as fast as I did it here. But here's the answer. Crappy situation. If you don't believe this, by the way, just take this derivative. You will see that is correct.
Isn't there supposed to be a minus somewhere? Since you actually have to the power minus a half.
No, because that's true. Well, yes, that is true. mean, you're right. There's a power minus 1/2. Yes.
Yeah.
But the antiderivative of that would have +1 in the exponent. So it will give you this thing to the power +1/2, right? But minus 1/2
right.
+1.
Oh.
So that means that in doing the differentiation, you don't pick up a minus, so I don't have to correct for it. Anyway, this is the solution. But here's an issue. Extreme fun on the train when I was doing this. Because look what happens. You know what a logarithm looks like, right? I mean, it goes something like this. This is minus infinity, and this, albeit very slowly, goes to infinity. I have to put in infinity and minus infinity. Now, of course, in order to really understand what comes out of this, you have to do careful calculus and limits and everything. But maybe you can already see that if you put in infinity, you get, okay, compared to y, which is a non-infinite number, z infinity squared is bigger than y. Okay, you take the square root of that. So for all practical purposes, if z is going to be infinity, the y might as well not be there. That gives you z squared square root, which is z, plus another z, which is also infinity. You get infinity plus infinity, of which you take the logarithm, which goes to infinity. That sucks. That's if you plug this one in. How about you plug minus infinity in? Right? You know this, right? You put the infinity in, you get some number out. You put the other one in, which is minus infinity. You get two numbers, subtract them from each other. Now, one of these numbers is going to be infinity. Hopefully, the other one will cancel that infinity.
What doesn't go to plus infinity?
The other one does is
not the end. Because you take infinity in minus the other one, and because it's like minus, the minus that it's like plus infinity.
And minus infinity. Yes.
So it goes to.
Yes.
Everything is plus.
Yes. Infinity. You're absolutely right. There's two ways of seeing this. Your reasoning is.
But it goes to 10 and 0 in this case.
No, but look at this.
I'm using his argument. It's squared. So squared is always plus.
There's a positive, and then you get
yeah,
square root of that, and then it's going to be minus.
Yeah, but he's right. It's always it's like the first term minus the second, and it's minus c minus c is plus c, and then you have that's minus.
That's. I mean, you're completely right. That's exactly the way it is. At the moment you plug in, I'm just using your argument. If the moment that you put minus infinity there, well, the square just will cancel the minus. Okay. Now we saw before that if this is going to be infinity anyway, might as well put your hand here. Forget about the y. You get infinity squared square root is infinity minus infinity because it's now minus infinity. Okay. So what you get here then is a logarithm of 0, which is minus infinity. Okay, maybe with this one, but then you get infinity and another infinity. You get two infinities. The two boundaries both give you infinity. There's another way of seeing the exact same conclusion. That's the way that I did it on the train. So much fun on the train always. Exercises like this. For some reason, never ever somebody sitting next to me when I do these things. Namely, if you use this trick, that the logarithm of a minus the logarithm of b is the same as the logarithm of a over b. Right? You can easily prove that for yourself by taking the e to the power of both sides. Now, what I have exactly that situation here, because I have a logarithm from which I have to subtract another logarithm. So I would get this. I would get the logarithm of z plus y squared plus z. With all these z's have to be infinity, divided by z plus y squared plus z, and these z's have to be minus infinity. Agreed? Same expression as this.
Yeah.
Okay, now we already saw if you put infinity here, you get infinity plus infinity. So the numerator is infinity. If you take the minus infinity here, you get infinity minus infinity. And again, you have to be careful about these things because you cannot just say infinity minus infinity is 0, but in this case it is. You get infinity divided by 0. Now infinity already is infinity, and if you divide something by 0, it becomes more infinity. Okay, so this becomes this huge infinity. That sucks. That means our scalar potential that we are calculating is infinity. Huh. So now what? I mean, I just did the math, okay? I didn't smuggle anything in. I just did the math. Huh, problem? Now, does anyone have an insightful comment what we should do now, or where does infinities come from, except for the mathematics? Did we break one of our assumptions maybe that we put in all of this in order to get this formalism in the first place?
Does this have to do with the Dirac delta function or not?
Well, the Dirac delta function, of course, is a thing that becomes infinity, right? At one particular point. But unfortunately, this is infinity regardless of how far your y is. The Dirac delta only becomes infinite at one particular point in space. And this one, regardless of what you put in for y, will become infinity. So it's Dirac delta-ish. Unfortunately, it's like a Dirac delta function at every point in space. Huh.
No, how we set our coordinate system, that can't affect it. This kind of.
No, there's many ways of seeing that. The simplest way I would say is because the y is infinite, this point is exactly the same as that point. There's no preference for points if the line will look the same everywhere. So that could not be the issue. How about this? While you ponder over this, let's pretend we never tried this integral. Oh yeah, please go ahead. Maybe
it's maybe the integral one. Is it from infinity to infinity?
Okay.
Because in the book I saw something that when something is like, normally we always assume that like the wires are like defined.
Yes.
But in case it's not defined, we should take it from the source, like not from infinity.
That is a very good point. I mean, of course, this is physically not true, right? You cannot have infinite wires. You can have long wires, but not infinite wires. So there's probably, we're breaking something there. Of course, but how would the mathematics know about physics not liking infinite wires? But there is some mathematics involved. I cannot blame you for not knowing this, but in order to go from here to all these things, we make use of a couple of these vector equations that are on the inside cover of the Griffiths book. Right? You have the gradient theorem, divergence theorem, you have the double integration, the double derivatives and such. These integral ones only work if your vector field of which you're integrating will go to 0 at some point. Now we have a situation, so the mathematics, if you just do the derivation of these rules, not all of them, but most of them, they only work under the assumption that the vector field over which you're integrating will go to 0 at some point. In our case, it doesn't, because the y is infinitely long. So that means that some of the mathematics that we've used to rewrite this into this is not allowed. That's the issue. And of course, physically, that's the same thing as saying, well, the infinite wire doesn't exist. Because the infinite wire physics does not exist. The mathematics also happens to break down, so I see no issue per se. I mean, it's completely how I would think that these things would work. So there's your issue right there. What I wanted to do was let you ponder over this, but here we are, we have the answer already. Let you ponder over this, while at the same time, just not doing this integral. Right? Just leave it in its integral form. Do this trick as if there's no problem whatsoever. All clear blue sky, no issues, blah, blah, blah. And then just do this and see what we get for the electric field. Maybe this is infinite. If you take its derivative, it's not infinite anymore. That sort of feels okay, right? Because the only reason that we get infinite here is because we are doing an integration. But this thing is sort of canceling the integration, maybe. So maybe we get rid of the infinities. The answer is yes. We're going to do this, this one here without doing the actual integral. See what we get then, and then we see that all the infinities mysteriously have disappeared. This is not a general rule, mind you. It's not that always when you have an unphysical situation and you have, unphysical results for your scalar or vector fields, that everything will go well at the moment that you calculate your actual E and B fields. It just happens to be okay in this case. Yes.
So if you would change the integration like from say a to infinity,
Yes.
they would work on.
I've tried that actually, because I thought, well, maybe what we can do is let it go from minus a to plus a. No, let's do it right here, right now. Right, so it's not an infinite wire; it's a finite wire. And then our phi, using that trick that I used before, with the rewriting of the logarithms. Again, I've done this on the train, so it's not like I'm thinking of this right now. Was the logarithm of this thing, with the upper limit being a and the lower limit being minus a. Okay, then you get a plus y squared, a squared plus y squared plus a divided by a squared plus y squared minus a. You would have gotten this. Right? Yeah, I just plugged in, where was it? Took this thing, put in a, put in minus a, subtracted them from each other, use this logarithm trick, you get this expression. I was hoping that maybe once you have this, and you then take the limit of a goes to infinity, it will be okay. It still doesn't work. We have now solved a different exercise, by the way. We've now solved what the potential would look like in a finite wire. There's the answer. That one happily exists, but then again, that's what we would expect, right? Because we don't have an unphysical starting situation. And, or, mathematically spoken, we're not integrating, we're not using a mathematical trick in which the thing of which you're integrating does not go to zero. Again, that's the reason why some of these integrals work in the first place. So we've actually now solved a different situation. So that's good, we've done 2 exercises now. Okay, but I proposed to leave this crappy integral here with the minus infinity and the plus infinity, just never explicitly try to calculate what it is, use the fact that here's a the gradient, hopefully it will just cancel out the integration, and as a result will not become infinity anymore. And if all goes well, we should get back the electric field that we've calculated in exercise 2.13. We've already done the exercise using this. Let's see if we can get the same thing out. So we're going to leave the scalar potential as is, minus infinity plus infinity, 1 over, let me just already put in that r is z squared plus y squared square roots. And then integrate over the z's. I have no idea that this thing will go to infinity. La 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 la, I'm not looking. Let's calculate the electric field. And as you know, what's wrong? As you know, the electric field is given by minus the gradient of this scalar potential. Let's see what we get. Well, I see some minuses cancelling, so that's good, I guess. I haven't done anything now. I've just taken this minus, cancelled with this one, and then I put the gradient here. Next step, suggestions. Oh no, you should be very careful with these things.
Oh, because of it?
That's not the reason. This is a scalar. So that's not the issue. You're right. I mean, that's what I've sort of hand-wavingly been saying up to now, that the gradient and the integration will cancel each other out. But we should be careful now. It's a point that I made a couple of days ago as well.
Separate the z and the y first, and then do.
Oh, that's a good idea. As in write this fraction as a sum of fractions, say.
Some.
Okay, sure, we could do that. But let me get to his point first. The reason that you cannot cancel this one against the integration is because this derivative does not work, does not operate. No, let me rephrase. The point that I made a couple of days ago was that you have an integration variable, and apart from that, you have your derivative variables, and they're not the same variable. Do you remember that when I mentioned that? A couple of days ago, I had an integration where I also took the gradient of. Then I said, but the gradient is derivative with respect to my position, whereas within the integral, I'm looking at your position. Now, you cannot cancel derivative with respect to one coordinate with the integration variable of the other coordinate. So you have to be careful about it with these things. Let's be very explicit about this. Which variable are we integrating over here? Okay. Let's just to be very clear. Let's give that a little prime. The y, whose coordinate is that? Is that the y's coordinate of which we're integrating, or is it my coordinate? That's my coordinate. So that means that this thing will only operate on the y's, not on the z's. Ridiculously careful with these things. Okay, now fortunately things become simple. Now this thing can just go inside the integration, yes? Again, because this thing is derivative with respect to my coordinate and the integration with respect to some other guy's coordinates, so they don't feel each other. Just take it inside the integration. And you have to take the gradient of this thing. Are the difficulties here? Just performing this step. Forget about the integration. Just this step alone. Know what gradient is, yes? Take the x derivative of that thing, put that in the x component. Take the y derivative, put that in the y component. Take the z derivative, put in the z component. What you end up with is a vector. Does this thing have any x components? Okay, so that means that the derivative with respect to x is going to be 0, so that thing that has to end up in the x component of the resulting vector is 0. Does it have any z components? You say no?
No.
Okay. I saw some people nodding and I saw some people shaking their heads. The answer is no. It has z prime components. It has a z prime dependence. It does not have a z dependence. I have to take the dz of this thing, and whatever comes out is the z component of my resulting vector. Now the dz of this thing is going to be 0 because there's no z's in there. There's a z prime in there, but not a z. I'm taking the derivative with respect to my coordinates on this thing that only contains some other guy's z coordinates. So that is 0. There is a y component. Derivative with respect to y of this thing. Difficulty, problem? So this is it, yes? This is what I mean a gradient. If you look here, it just says the y derivative of this thing. Oh, and of course everything then has to be integrated over dz prime. Need some extra space here. Anyone wants to tell me what the derivative is there?
Is it not y over the argument on that?
I heard you, but I didn't parse. Can you say it again?
The derivative of this argument.
Yes?
It's like y over the square root of
Yes. Yeah. Thank you. With a minus sign.
Doesn't it cancel out?
No.
Because you have minus a half.
No,
And
no
then-
minus.
Oh no, yeah, actually no, it doesn't cancel out. No.
Why is the minus?
Because it's over square root, so it's going to be minus a half times that, and then times general.
Yeah.
Okay, and then what you end up with, you're right, so there is a y, that's true, and in the numerator you will get z squared plus y squared, careful now, to the power 3 over 2. This is still 0, this is still 0, there you go. And this whole thing still has to be integrated over these z prime. Let me write it somewhat suggestive way. For pi. Might as well take the y outside of the integration because integration is with respect to z's or z primes. So the y can be taken outside. Integral 1 over z primed squared plus y squared 3 over 2 dz primed. Oh, minus infinity. Oh, minus infinity plus infinity. Yes. There you go. Okay. It might look familiar now. 2 weeks ago we did the exact same integral. Of course, I can hardly blame you for not knowing every single formula from 2 weeks ago by heart. But we have already done this integration. I think you looked it up even. Remember that? Use of online integration. Well, I mean, of course, you don't remember what the outcome was.
Yeah.
Right.
Let me write somewhat more suggestively. Z primed squared plus y squared to the power 1/2 is what we call r. You have 3 of those here because you have 3 over 2. So this is really r to the third. But r to the third, you can take 1r off and divide the y. You get the unit vector in direction y. You will get this. Right? Hat means unit vector, it just means in that direction. Get it inside again. And because I've taken one of the r's to make this a unit vector, I have 2 r's left. That's that one. Z primed. This we have done before, this integration. Let me just give you what the answer is. If you think that's cheating, just look back to the recording of 2 weeks ago. Because there's no physics involved at the moment. This is just doing the mathematics, and we have already done that. So let me just give you the answer. It's this. Zero, and you'll get a y squared downstairs. This is the answer. Again, see your notes of 2 weeks ago when we did the exact same integral. The y squared comes because of this integration. There is already a y here in the top. So you get a y here, 2 y's there, they cancel each other out. And you have this expression for the electric field.
But what happened to the z dash then?
Oh, the z, at the moment that you do this integration, you get the antiderivative, and for z dash, or z primed, you have to put in infinity and minus infinity, subtract them from each other, so the outcome will never have any z's in there anymore.
Okay.
Notice that this is not infinity. So even though our scalar potential was infinity, if we just closed our eyes and just went on with this trick here, we got the final answer. But not just that, it's the exact same answer that we got 2 weeks ago, when we did the exact same exercise but using these tricks. If you're going to compare this to how we did it 2 weeks ago, there was one small difference. We call this distance S. But apart from that, it's the same exercise. Any questions? It's the mathematics, isn't it? Mostly the difficulty for some. Yes?
If we consider scalar potential in Griffith's context, which is potential energy per unit charge,
Yes.
then isn't saying the scalar potential is infinite is blasphemous?
Because it was okay. Yeah, I love these questions because it translates the mathematics back to physics. It's a good question. If we are to read this as the potential energy of the electron or so. Yes? Then, okay, forget about the electric field. We get an infinite amount of quote-unquote energy here. Right? That's your question. Isn't that blasphemous? I like the phrasing, by the way, because we don't like infinities in physics. Okay. I don't think it is. Well, I mean, it's blasphemous in the sense that it's not physical, but it does agree with the situation. Because let's read just for a second what we meant by before when I said that the potential energy you can see is Q times phi, right? I said you have to be careful with these things. It's not exactly true, but at the very least, this is 0. So whatever the potential energy is will not depend on A fields. So let's just assume that this really is all the energy that I put in, the work that I've done is all converted into the potential energy of this charge Q that I've placed at this position. Okay? Now how much charge is there along the whole wire? The wire is infinitely long, and every piece contributes a certain amount of lambda. Infinite. Okay. So what I'm saying here is I take an electron from somewhere in space, then I move it through space all the way till it gets here. And I ask the question is, how much energy will that cost me? Well, an infinite amount, because there's an infinite amount of charge that I'm pushing against. So it's blasphemous in the sense that it's not physical. But the answer does agree with my intuition of what this thing is. Now, if it's not an infinite wire, if it is wire, you can immediately see, okay, it will cost me energy, but not infinite amount.
But are we not getting infinite because we're not using the proper, like the formulas we're using are not made for this?
That's true, so it's sort of a shaky argument. Right? Again, the integration rules that I use to go from here all the way to here are only proved in case the fields go to 0. So it's more of a happy coincidence that they apparently still work. But there's an important point here, I guess. The rules that we used certainly work at the moment that fields go to 0 in infinity. That's not the same thing as saying fields should go to 0 in order for them to work. You could probably still make situations where even though the fields do not go to 0, that particular integral will still work. Right? It's not a one-on-one correspondence that they have to go to 0. There are proofs for that case, but it's hard to tell at this point. Consider it a happy coincidence that we could still use the formulas. Okay, take-home message. Don't worry too much if your scalar potential happens to be infinite. It might just well that they're cancelled out against this.
One question.
Yes.
I'm still not sure how to visualize the C prime at the beginning of the problem. Like on my own, I wouldn't have figured out what would have just using C with the prime.
What is the question exactly? There was something about the Z prime, yes?
Yeah, like where in the diagram would it be? How would you visualize it on the diagram of the...
Oh, okay. There's 2 Z's in my diagram here. There's a Z that I happen to have here, because this is where I'm standing, that's Z. But the integration tells me that I have to go over every piece of charge. Now the position of every piece of charge is called Z prime. So this lambda is at position Z prime, and I'm at position Z.
Yeah, okay.
So that's it. How about we do a magnetic one? We've also done this exercise before. That we took the exact same situation, but instead of a charge in there, we put a current in there. We calculated before what the B field was. It took us more trouble because we had to take an outer product because of the Biot-Savart law, if you recall. You have to take the outer product of the current and the unit vector. And it took us a little bit longer, but ultimately we got the B field. Let's see if we can do the same thing, but now using our potentials. So again, same situation. A wire that runs from -infinity to plus infinity, and instead of wanting to calculate the B field, we calculate, the E field, we calculate the B field. And there's a current running through the wire, what we call I. We're going to calculate how much magnetic field I feel at this position. Oh, by the way, in what direction did the electric field point, if you did the calculation? Yeah, pointed downwards. We already suspected that before. We've done it. We've seen it mathematically happen when we did this. We see the same thing happen here because that only has a y direction. And that, of course, makes sense. Okay, what point will the B field point at this? Yeah. Oh, this is all the right hand rule, and some people use the left hand side rule, right? Regardless if it's going to be sticking inward or outward, it is going to stick in X direction. Yeah. There's many ways of seeing this, but
which way does the car go?
This way, along the wire.
Why is it? Okay. Yeah, no, I can't. I've learned it this way, but it doesn't work for me.
Okay.
If you use the right tool.
Not sure how your teacher taught it in high school or someplace else. I mean, I guess everybody makes up their own rules.
No,
but
how was it again? I think he taught it to me like that's direction of the current. That's the direction of the magnetic field, and this is the.
You see, you didn't see. I can't remember.
Tennis and physics doesn't work.
I remember near magnetic.
Yeah.
Okay. The idea was. This is probably how you were taught this in high school, that if at the moment you want to calculate in what direction a particle is being pushed as it flies along.
Oh, it does make sense. Mine.
Sorry,
yeah, it makes sense. Sorry.
Oh, okay.
Yeah, mine.
Still repeat my sentence, that at the moment that you want to calculate in what direction a charged particle is being pushed, then, at least in my high school, we were always taught that you have to take your right hand, then point this one in the direction of the force. This will go into the direction of the magnetic field, and then this one, right angles of all of each other, this one will point in the direction of where the particle happens to be flying.
Yeah. And
then you do this. But this is not our question here. I'm not asking about force. I'm just asking where the magnetic field is. For this, you use your left hand, at least in Dutch high schools, if memory serves. And the idea is you curl it like a little claw, right? And what you do is you point your thumb in the direction of your current, and then the direction of your little claw will tell you where the magnetic field is.
Oh, shit, it's the left hand.
I thought it was the
I
right
remember
hand.
it was the right hand, but the same thing goes with the
no,
right
really?
hand. Like the
I think it was
current goes in
right
that
hand.
direction and then the
Okay, well, okay,
Yeah,
but
it
it
goes
might be
around.
okay. But there's convention here. Not to smuggle away minus signs or anything, but there is really a convention, namely that.
Or
if
electron
you-
current or current.
Yes, I mean,
Yeah.
if you're talking about the current in the sense where do the electrons flow, then you have to use your right hand.
Yeah.
But if I means where would the protons flow, or the plus
okay.
charges, you would have to use your other hand.
Okay.
Anyway, fortunately, we don't have to do all these little ghetto tricks, just the gang signs and everything. We just do the mathematics, okay? Yeah.
Yeah. Physics. Yeah.
Oh no.
Ghetto physics.
Yeah. Experimental physics.
Okay, so what object to calculate first?
Yeah, it's engineering.
Want the B field? Yes, let's calculate the vector potential. We don't need the scalar potential, not just because it's a static situation. Of course, there's something flowing, but the B field will be the same everywhere. So in that sense, it is static. It's not just because it's a static situation we only need A. You never need the scalar potential to calculate B. Not even the dynamical situation. So really the only thing we have to calculate is our A field. And we know the differential equation for the A field. And the Lorentz gauge, that's this one. And because the A itself is not changing, steady current, this one is 0. So that means that the only thing we have left is this. That's a differential equation. And 2 days ago, we proved what the general solution is of the differential equation. In fact, it's just right here. So No thinking required. Just copy paste our general solution there. J R primes. Be mindful again of where the primes go and what all the different R's mean. Integrate of all volume. Our R is still that same object as it was before. And one final step before we can actually go and do some calculations is, instead of saying current times volume, you can also say this current, line current, times length. So it gives you I, still a vector though, R primes. There you go. I'm just going along the wire now. You look troubled.
Like, why didn't you just use the general solution?
I did, didn't I?
But then where did the mu 4 pi come from?
I have forgotten to write it here.
Okay, that helps a lot.
Yeah, yes.
The minus sign.
What is the minus signs? Oh, that's because the differential equation comes with a minus sign.
Yeah.
And the solution cancels it. Remember this. What we proved 2 days ago was if you have this differential equation, and the solution is given by minus O1 over 4 pi s r prime over r dv. This is what we proved 2 days ago. So the solution comes with its own minus sign. That's the minus sign I'm writing over there, and I see that I made a mistake here. The minus sign should not have been there. I'm so sorry.
Oh, okay.
Yeah, so sorry. Because that minus sign was already cancelled by the minus sign that comes with the solution.
Okay.
And yes, and I also forgot the mu 0 and the epsilon, so. Okay, the epsilons and the mu
Does that mean we made a mistake in the previous one?
No, because the only thing it changes is an overall minus sign and the presence of a mu 0 or an epsilon 0.
Okay.
So if
So they're just constant. Sorry, those were no, it's my fault. But let me just make this sentence. The only thing that I missed before was a constant. It did not change the integrations, say. It's not like I forgot x's or y's or something. The integrations are still the same. Just plug in the missing epsilon and you'll get to the answer. Yes. Sorry, Jules.
isn't that A supposed to be mu 0 or 1 over mu 0? Which one was it?
It's mu 0. Okay, well the mu 0s and the epsilon 0s I can sort of talk my way out of this because as some of you already know in theoretical physics you put everything to unity, including the speed of light. You know that mu 0 and epsilon 0 are related to the speed of light. So if you take the speed of light to be 0, you might as well take mu 0 and epsilon 0 to be 1. And that's what I use in my private notes, so I forget to write these things down all the time. The minus sign, not so much. that I can really not justify in any way. Well, in theoretical physics we use it, -1 equals 1. I mean, that doesn't happen. Okay, but this is now correct, I think. Yes, including, this is correct. No minus sign here, because this minus sign will cancel against that minus sign, and the mu 0 is at the right place. This is correct now. Okay. Okay, well, the I. We have an expression now for our A field. We can simplify it just a little bit more if you want, namely by saying that the exercise states that the I is a constant. There's an equal amount of current everywhere in the wire, so might as well take it out of the integral. You have to be careful, it's a vector. It's different from the scalar potential before. Now what direction does it point in our coordinate system? Exactly. And no x and y directions, yes? So might as well write it like this. Oh, here's some interpretation of a vector field for A. The vector field for A, if you look at this thing, vector potential, will always point in the same direction as your current. So, right? I mean, it's sort of the magnetic field, but now not pointing in strange directions using some sort of gang signs or anything. because this general solution is always in the same direction as the current is flowing. If you want, you can read something into this. Bless you.
Sorry.
What I'm going to do, I'm going to take all of the vector part outside of the integration. So it's 0, 0, 1. Why 1? Because I'm going to put the I over here. Then my integral is 1 over r dz. And notice I'm switching between z and z. Take your pick which one you like the most. Oh, oh, look at us being in a crappy situation again. Remember this integral? Yeah. It's the exact same integral as we did in the electric field. Why? Well, because the integral just comes from this general solution, right? This one. And it always comes with an r downstairs. Does it mean that all of these are going to be infinity at the moment that you integrate from minus to plus infinity? No. Because there might very well be something in the numerator that will cancel out the infinity. It's just
a constant now. So
yes. In our two situations, both for the charge wire and the current wire, there were constants. And that's the reason that you get the same crappy result, namely infinity. Yeah, that sucks. But then again, it doesn't, because we saw before that if you just pretend that you're not seeing this and you take this curl, you still get, or at least in the electric field, you still got the correct electric field. Let's see if the same thing happens for the magnetic field. So let's do that, and then have a break. Look at the magnetic field. The magnetic field you calculate from the A field. We have the A field now. Of course, in integral form. The unintegral form is infinity, but pretending that we're not seeing it. So we just have to take the curl of that thing. Agreed? You have to be ridiculously careful again. The curl are derivatives with respect to my coordinate, but the integration is with respect to this guy's coordinate. So that means the integration and this derivative curl do not feel each other. You might as well take the curl inside of the integration. That's what I do here. Now curl has to operate on a vector. We saw that the vector is this 0, 0, 1, but this 1 has been multiplied by r, which is this expression. So that's this. Now you have to take the curl of that thing.
Question: where did the vector go after the I? Did you just get rid of that?
As in, okay, it was a vector here.
Yeah, that one. Where did that go?
It's here.
Yeah, but it still should say 0, 0, 1.
You just took out of the vector.
But shouldn't there be like an arrow on the I?
No, because I said that I only points in z direction. So this vector 0, 0 has an I z component, but this is not a vector. It's how much current there is in z direction, which is a number.
Yeah, so
if this confuses you, just call it IZ, the amount of current in z direction.
No, it's more like that we wrote it like that earlier. Like the
001?
Yeah, the 0, 0,
yeah,
1.
but that's still the same thing, isn't it? Because multiplying this vector by I would just put the I here, which is exactly that. So
yeah, sure.
I mean, sure. I mean, sort of switching from notation to other
exactly.
notation.
More like because we don't write it down the same way as we do there.
No, that's true. But do you see that it's the same thing?
Yeah, I do.
Okay,
I do.
good. Okay, we have to calculate the curl of this thing, and then after we've done that, we have to do the integration. you fluent in curls? Can you just write down a curl just without having to look in some book maybe? General advice. It would be good if at some point you have no difficulty knowing what a curl is or how to write down that expression. Well, for one thing, you know, it's going to be a vector that comes out. Because curls give you back vectors. So we'll have 3 components. Now, using our gang sign, we already know that D is going to be 0. Because it's going to point in X direction. It's going to point either inside the board, which is along the X direction, or out, which is also along the X direction. So using the gang sign, where we know that these are probably going to be 0, but can we see it from the definition of the curl? Tell me.
Because if you just like do it, you'll see that you're gonna try getting derivatives of things that aren't in that other vector.
That's good. The X component of a curl is the Y derivative of the Z component of this thing. And some extra term that we'll write down in a second. Sorry, just switching up notation again. Is it okay for brevity's sake that I write this as 1 over R? Okay. Curl means take the Y derivative of the Z component minus the Z derivative of the Y component. Now the Y component happens to be 0, let alone constant. So subtract 0 from this. That's the X component. Definition of curl also says that the Y component is the Z derivative of the X component, the Z derivative of this thing, which is 0, minus the X derivative of the Z component. Now there is a Z component, but it doesn't depend on X. So this is 0 minus 0. And again, definition of a curl. The Z component is
X derivative of the Y component.
It's the Y derivative of the X. Let's see.
It's the X derivative of the Y minus the Y derivative of the X.
Okay, but both are 0, yes?
Yeah.
Yeah.
So
Okay.
it doesn't matter.
Right. So that agrees with our left-hand rules or right-hand rules. In fact, this is where they come from, of course. The left-hand rule is just another way of saying the curl. So here, this is why it's called curl, by the way. Eye opener. This is why it's called curl.
No.
Yeah, I'm serious.
No.
Really?
Yes.
I don't believe that.
No, okay, not because of somebody, actually some mathematician at some point said, you know what, let's take your hand and curl it in a certain direction. No, but if you think about it, if you take the Y derivative of Z minus Z derivative of Y, what you're really doing is saying how much of your Y has been turned into Z.
Mm.
And that is, of course, rotating, right? Another word for curl is rotation.
Yeah.
Maybe, okay, rotation, would that be a better word to use? And then maybe some other guys at some point, oh, it's like curling your hand. Let's call it curl or something like that. But I mean, that's what it does. Okay, so good news. We have now found that the B field is along this line somewhere. And the rest is just doing the remaining integral. Well, it's going to be a vector that only has an X component. So let me write it like this. A vector has only an X component. And what remains is this. There you go. Right, and you calculate this, whatever comes out, you have to multiply either by 1, that will just give you this, or multiply by 0, that gives you that and that. Almost there. But there are 2 steps. So let's take the Y derivative of this thing, and once we have that, we integrate it over Z. Now, fortunately, we've already done the Y derivative. Recall. recall what it was from the previous exercise. Let me just write down what it is. It was a minus y over r to the 3. The z prime to minus infinity. It so happened that during the electric exercise before, we found the same derivative. Then we have to know what this means. Put back in what r was. R was y squared plus z prime squared to the power 3, 2 dz. Just plugged in back what r is. Because of the derivative, it's now to the power 3, so it gives you 3 over 2. Now you either look up what the integral is, or maybe you know how to do this if you play around with it a little bit. This was the integral a couple of weeks ago Chai knew how to do. He emailed me about this. This one. This one you did before.
It's the same as.
Do you remember what the answer was? I mean, physics is done now, yes? I mean, this is just doing the rest of the integration.
Isn't it the same as the electric field?
No. Was it?
Because
Same as the electric field?
y over r cube and then y divided by r is.
Do we have the exact same one? Really? Is it that simple?
Yeah.
Okay, so what is the answer?
Well, you can convert it to y hat over r squared
Yes.
first.
Yeah, it is the same one. Yeah, exactly. Of course, it's because the situation is so ridiculously similar. But yes, you're right. We already wrote it down, but I forgot what it was. I think it was this. I think it was y squared. Yeah, it was y squared plus z prime squared. I think it was square root. I think there was a z here. I think that was it. The integration. Let me go check. I think this was it. Yeah, it's exactly this. This is mathematical stuff. We did this one before, 2 weeks ago again. I also used in the electric one where I just smuggled a little bit. I said, remember that was this? This was it. But you have to put in minus infinity and plus infinity for the z primes. Maybe you will call that this is the same as 2 over y squared. Take a moment for yourself that you actually see that the last step is true. That's you. Take z prime. Let it go to infinity. If you let z prime go to infinity, the y might as well not be there. You get z prime divided by z prime squared, or in other words, z prime divided by z prime, cancel each other out. What remains is 1 over y squared. From that, you have to subtract the same thing with minus infinity. It gives you minus 1 over y squared. 1 over y squared minus 1 over y squared is 2 over y squared. Okay, so we have done this thing now, ultimately. 4 pi, 1, 0, 0. All of this we have now done, took us a while, but here we are. And gives us another 2. A y squared downstairs, but be careful, there was already a y here. So there is a y there. A couple of y's cancel each other out.
Wait, can you say that again?
Yes, when I did all this stuff here, we found that there was a y because of the derivative that we had to take. Right? There was a derivative here, and that left us with a y in the numerator. Then I did this integration, which gives us 2 over y squared. So there's a y in the numerator and a y squared in the denominator.
Yeah. Oh, you took the y out before you did the...
Yes.
Yeah,
Yes.
right. Okay.
So ultimately, your final answer will only have 1 y in the denominator. And the 2 that you have in the numerator will cancel the 4 here. 2. And now we have our magnetic field. Yes?
Before we were treating I as a vector, and
Yes.
in that board we stopped treating I vector.
Yes.
Shouldn't we have kept the I as a vector?
But I did. It's just I renamed it. It's a vector here, yes?
Yeah.
Then I said, well, but this vector, because I know from my picture that it points only in z direction, I just call it 0, 0, iz. So from this moment on, all the vector parts are just written in front of the integration. And the number that is here, I wrote here. I never did away with my vectors. The only
No,
thing
it's
that
just a different notation.
Yeah, but the I still only has a component in Z.
yes.
Wouldn't that interfere in the final result?
Why?
Because in the final result you've got the direction of the magnetic field, but shouldn't you still have the 0, 0, 1 of the I?
No, because the curl changes direction of things. That's what curls do.
Why?
That is very little to do with physics. That's a mathematical fact. That if you take the curl of a vector, you get another vector, but it points in a direction perpendicular to the one that you started with.
And that's where the field points out of the.
Yes. Because explicitly you saw it happening here. From here to here, we took the curl, and then we saw that the only surviving component was the x component, even though the current itself was a z component.
Okay, yeah, I see it now.
Okay.
In the 2 over y squared, where does the y come from? That cancels the y squared in the bottom.
It was written here before. We took the derivative here.
Don't you already account for that y inside of the integral right below it?
Yes, and we are being very sloppy in my notation here because here's a y and I forgot to write it here. Right? The integration that I did here was as if there was no y already in the numerator. So I'm just being sloppy with my notation. So for the viewers at home, okay, there should have been a y there. And we should have canceled this one.
The viewers at home.
Yeah. No, I'm being sloppy in my notation, I agree. But this is correct, the way it's written down now. This, by the way, this answer that we have now here for the B field, including its direction, is one that we also did before, 2 weeks ago, but using these tricks. Again, take-home message here is, first of all, you can do it using the potentials, works just as fine. Even if your scalar vector potential here itself did not really exist. It was infinite. Just pretend that it isn't, do your tricks, you get the same answer. High time for a break, I think. How shall we continue? There were some mathematical exercises that are important. These are just applications. One that I particularly find interesting was exercise 10.7 from Introduction to Electrodynamics, where you have to do the same trickeries that we've been doing now, but now for a dynamical situation where these things are not zero. It's the same mathematics, it's the same physics, it's just somewhat more involved. I do propose to do that at some point, but I don't think we have enough time for today to do that one, so just leave it for now, I guess. Yeah, exactly. So let's do one of the mathematical exercises. Yeah.
I thought we finished at 4.
No, the new tutorial says.
Yeah, we can finish at 4. Okay.
I mean, if you want to.
Yeah, I'll just stand here by myself and talk to the empty room about electrodynamics. I do this all the time in my office, by the way. Yeah, let's do one of the mathematical exercises. Particularly, I think, well, unless you have a suggestion or a preference, what I would like to do is take the more difficult differential equation for phi and for the A field, use Lorenz gauge, and show that you actually end up with these equations. Right? It's a claim that I made 2 days ago. I haven't actually proved that was the case. One other thing that is worthwhile to go through is what gauge choice did you have to choose in order to make the Lorenz gauge? By this particularly, I mean, if you recall, you can add to phi, you can add to A any other thing as long as it's the gradient of any function, lambda. It will still give you the same magnetic field. And then we showed a couple of days ago that in order to also get still the same electric field, you're obliged to take this one and subtract the time derivative of the same lambda. As long as you do this, you will always get the same electric and magnetic field. And we use this freedom, this gauge freedom, the choice to choose your lambdas in such a way that our differentiation becomes easy. Then I made the claim, okay, using a particular choice for lambda, you get the Lorentz gauge. What I have not done is shown that such a lambda exists that gives you the Lorentz gauge. It just said, well, given that it exists, such and such. So there's two steps now. One of them is, given the Lorentz gauge, and just to remind you, the Lorentz gauge meant that you choose your lambda in such a way that the divergence of lambda is minus this. Then you end up with these two simple differential equations. That was claim one. And the second thing we have to do is, well, is it possible to choose a lambda in such a way that this will hold? So there are two steps. I propose to first start with saying, well, assuming that lambda can be chosen that this will hold, do these different differential equations for phi and for a, reduce to these simple ones. And the interesting question is, how should you have chosen lambda? Can somebody remind me what the differential equations for the A field and the phi field look before you've chosen your gauge? Because they're big and I don't know them by heart.
Like, which of these other questions is it?
Is it E, I think.
E.
Didn't we do that?
No.
No, we didn't.
No, that we did.
That's something else.
Show the solution. Oh,
we
wait,
did
you're
E.
right.
We did E
It's
in
D
class.
then.
Okay, can somebody read out loud what D is?
Using the Lorentz scale, show that the transform is correct.
Yes, okay, sure. Okay, and then this other exercise, I think that was C, I don't know by heart. One of them
Yeah,
says,
it's C.
yeah, that says, well, how should you have chosen lambda in such a way that this Lorentz gauge holds? Now, first we're going to assume that it does, that a lambda can be chosen such that the Lorentz gauge follows. And given that that is the case, do you end up with these differential equations? And this is D?
Yeah.
Okay. Again, can somebody remind me what the differential equations look like before you have chosen the gauge? They're crappy and they're long.
I think it was the Laplacian phi
Okay.
plus the time derivative of the divergence of A
Okay, that sounds familiar.
is equal to minus rho over epsilon.
Right.
Isn't it divergence of the time derivative of A? Or does it not matter?
That doesn't matter because they're different coordinates, so you can take the derivatives in any order that you want. But you're right, you could easily also write this as first take the time derivative and then take the divergence. So we give you the same answer. And then there was the one for A, which is much more complicated. I think that starts with Laplacian A.
Yeah,
Yeah.
Laplacian A. Minus the gradient of the divergence of A. I forgot the word divergence.
Of A?
Yeah.
Yeah.
Okay.
Is equal to minus mu 0 j plus epsilon mu and the time derivative of the gradient of phi.
Phi.
Yeah.
Are you sure?
Yeah.
Yeah,
Really?
phi.
I
Because
have
we
time derivative of E.
That's
Which
the
is
same thing.
that?
Well, wait. It's not quite the same thing. It was the time derivative of E, because that came directly from the Maxwell equations. But E can be written as this thing and that thing.
Yeah, so that.
So
Yeah,
some
and
of
then,
them-
there's another part
Okay.
which is plus epsilon 0 mu 0
Oh, yeah,
the
okay.
second time derivative of A.
Okay.
That's
Of A, yes,
Yeah.
exactly. And of course, this term directly corresponds to this one.
Yeah.
And all the signs are correct. So these are the ones before you've made your gauge choice. So this is before gauge. And now we're going to use the Lorentz gauge. And as I stated over there, the Lorentz gauge means that you chose your lambda such that the A field that you end up with equals minus the mu 0, epsilon 0. I think this is it. Can somebody check? Yeah, including the minus sign? Yeah, okay. Okay. just going to plug it in, aren't we? So two equations. Here's one. Here's two. Start with the one. By the way, why don't we just leave it like this? Why choose a gauge in the first place?
Because it's circular. Because the A is dependent on the phi, and phi is dependent on A.
Yes, yes, you're right. And the puristic way of saying this, it's a couple differential sets of differential equations. But circular, I like that too. You need one to get the other, but you need the other to get the one. And of course, if you make this choice, then they decouple. Remember, there was also the Coulomb gauge where this was just equal to 0. If that is equal to 0, then this will drop out. Then you would still have one differential equation that depends on both, but the other one does not, so you could solve this independently. So you would also gotten rid of your circular property of the system. But yes, the Lorentz gauge, of course, much more convenient. Well, let's just see what happens. Laplacian of phi plus this thing, time derivative of the divergence, and the divergence going to this case you can write as this. Epsilon 0. Note that you get two time derivatives now. One because there was already one, and the second one because of the gauge itself. And this thing is equal to rho over a constant. And it's now perfectly decoupled. This I'm really just testing now, but what is the solution to an equation like this? Always homogeneous. This is 0.
Sine, cosine.
That is one solution. We showed it explicitly for the sine, but it's true. Yes. But then we made a much more strong claim. Maybe it will help if I...
Something like any combination of sine and cosine?
Yes, it's still a solution because it's a linear differential equation, so a linear combination of solutions is itself a solution. And yes, exactly. A linear combination of sines and cosines is what mathematicians call a discrete Fourier transform. And then Scott made the argument, but wait a minute, can you? It's only periodic functions that you can write in this discrete way as a sum of sines and cosines. Yes, that's true. And then I said, but if you make it a continuous sum, every single function can be written as such, on the condition that you can differentiate it infinite amount of times. So these very mild conditions. And we use this to say, well, apparently all solutions to this thing will always be this. Have to depend on x or on r, if you will, position in space, minus v times t. And then the v is given by 1 over the square root of this number, which is exactly in numerical value the speed of light. And this is how we could conclude that apparently things move through space with the speed of light. This is what comes out of the theory. And this holds for any function. As long as it depends on r and t in this particular manner, there will always be a solution to this one. If only the signs were correct, then everything that moves through space electrodynamically will always be a sign. Okay, good. Now, this one has been checked. This one does indeed lead to this one. Let's do the second one. Laplacian of the A field minus the gradient of the divergence. But this divergence is exactly that thing. So now you get the gradient of this thing. No dots, no crosses, it's the gradient. What else is there? Equals minus mu 0 plus epsilon mu. So, plugged in the Lorentz gauge. And I see some good things happening. You take the red marker of cancellation. cancel each other out. Sure, the derivatives are in the opposite order, but since they are derivatives with respect to different coordinates, that doesn't matter, you can swap derivatives. Okay, so what remains is Laplacian of the A field, this I will take to the other side, minus second derivative. Look at this. There you are. And that proves this one. Again, this of course only holds if we know that lambda can be chosen in such a way that this holds. We don't have the time to go into it. It's really not that important to know what that exact lambda is, but it is important to know whether that thing exists. So it is a good exercise to go through, but we don't have the time right now. It is written in Griffiths somewhere. It's one of the exercises. Don't know which one it is because I thought of it myself. And then I saw that Griffiths also has an exercise. So I'll send you which one it is. And in case you want to go through it, it's in the solution manual. I will say this before we end. Last time you asked, so what is the connection to special relativity? And I made some points. And because we're going to see each other in 2 weeks, right? Because Jacco is going to take over next week. 2 weeks, I will tell you about the special relativity part. But as an appetizer, I'm going to give you 2 arguments. One I already gave. Namely, now I'll give you a second one. One argument that I already gave you was that in special relativity, it's very normal to have some observables having different values for one observer than for another observer. Right? Time and space, or to be very clear about this, duration and distance are different from one observer to the next. Right? If I measure something that takes 7 seconds, and depending on how fast the other guy is going, it might for him take 5 seconds. And if I see something that's 10 meters wide, then for the other guy it might be 7 meters wide. I'm talking about time dilation and Lorentz contraction. And that sort of sucks because that means if you want to do calculations in special relativity, you have to be extremely clear whose observation you're talking about. But the whole thing about special relativity is that you want to write down your physics in such a way that your conclusions hold for everybody. So the numbers might be different from one person to the next, but the relationship between these numbers have to be the same. And again, this is the appetizer. The way to do this is that you write everything as a column of 4 components. A famous example of this is the amount of time and the amount of space in 3 directions. Right, this combination of 4 numbers you call x mu. It's called a 4 vector. Now a 4 vector is not everything that you can write as 4 numbers in a column is called a 4 vector. In fact, not everything that you write in a column is called a vector. It has to have certain mathematical properties for a normal vector. And a 4 vector has a very special set of properties. Namely, that if you take one 4 vector and you multiply in a way that I will say, make explicit in 2 weeks from now, you multiply it in a certain way with this other 4 vector. It's called the other 4 vector A. Let's not call it A, because we already have an A. F. Okay? If you have shown that a certain set of observables can be written in this particular way as a 4 vector, with all the mathematical identities that apply to them, and you have one of these other 4 vectors, call it F, then this particular combination will be the same for every observer. Even if their components might be different, this particular combination will be the same. It's called invariance. Now, we exploit this invariance in many, many ways in physics. Here's a famous example. X mu is what we call the proper time squared. If you don't know what I'm talking about, don't worry about it. We're going to talk about it in 2 weeks, of course.
So, with the
yes.
interval.
Yes. Yes, this is still called the Minkowski interval, or just the interval, yes. So the dt's and the x and the y's and the z's in the interval are different from one observer to the next, but a particular combination of these things, namely all of them squared and then minus the time squared, is the same for all, even though their numbers a piece are different. Now, what we will see in 2 weeks is that this field and that field obey exactly the properties of a four vector. I did not put that in. I just used my mathematics to go from this to this. It's really just because nature had already decided that this was special relativistic, that people later on, wait a minute, if you write it like this, it becomes a four vector. And because you know it's a four vector, that means if you take a mu with any other four vector, that particular combination will be the same for everybody. It will be invariant. And this is something that people in special relativity love. It's hard to do physics if values change from one person to the next. So if you can find any number that will be the same for everybody, then you've made a huge step forward. Of course, in order to do that, you need four vectors. And it just so happens that these two things exactly form a four vector. No meddling required from me. Nature has done that for us. This is another reason why we work with these things instead of these things. Because these things do not form a four vector. In fact, you don't even have four vectors, you have six of them. 3E's and 3V's, right? With three dimensions each. But this one is a four vector. So that was argument one, how we're going to do special relativity in 2 weeks. The second one is this. If you're not following this, don't worry about it, by the way. And if you are, that's fine. If you look very closely, this particular combination of two derivatives with respect to space and two derivatives with respect to time minus each other is exactly of the kind of your interval, where you have x squared plus y squared plus z squared minus t squared. Remember that? Special relativity? That thing is invariant. Is that me? Somebody's calling. Now you can show that derivatives have the exact same property. That t derivatives and x derivatives, I'll be very explicit here, that if you put the t derivative up front, up here, and the other three derivatives down here, then this too is a four vector. I'm claiming this now. I have to explicitly show it mathematically in 2 weeks, but this is also a four vector. And what did I tell you? If you have two four vectors and you multiply in a certain way with each other, you get something that's the same for everybody. That's what I'm doing here. 2x derivatives minus 2 time derivatives. In other words, this four vector multiplied by itself. So that means that this whole thing will be the same for everybody. So if I've solved what A is for one person, I also know what the thing is for everybody else. So this general solution that I have here, in the static case, is not just good because we now have the general solution for any situation, because the derivatives form a four vector in this exact combination that make an invariant. This whole equation itself is invariant. In other words, the A that you found is even the same for all observers. So it's highly relativistic, this theory. Of course, Maxwell, when he did all this, he had no idea. It was Einstein who pried it out, who saw, wait a minute, something fishy is going on here, or something beautiful. Okay, this is for over 2 weeks. Jakob will take over next week. Still to do all this stuff, but with some time dilation. Not time dilation, time, what's the word here?
Delay.
Delay, thank you. Some time delay built in. It's called Jevtumenko's equations. He will talk about that in 2 weeks. I'm going to do the special relativity part. Recording will be uploaded tonight. Put a little synopsis there, and all the exercises that we haven't had time for, you can all find in the solution menu. Okay? Thank you.